after a long time we have a class with you. So let's see shear wall design. Actually, students requested me to take a class on shear wall design, and I have to study on a lot on it. And finally, I made a note for for you to share with you. So today we'll talk about little bit about the shear wall design. And you know that shear wall is very important for high-rise buildings, reinforced concrete buildings, to control deflection of the buildings mostly. And this note I prepared based on the notes I collected from AVM engineer AVM Sajjad Hussain and Professor Dr. Muhammad Nozrul Islam. So I acknowledge their support to prepare the note. Shear wall, you know that shear wall is a wall-like structural element. I think you already familiar with the shear wall. The how it is. It is a wall-like structural element. You can see here. This is a shear wall here, and mostly in plane loads like horizontal loads. It could be wind loads, and also it could be earthquake loads that we apply on the shear wall. That is the parallel to the plane of the wall. We generally apply the load, um, uh, horizontal loads in the plane of the structural walls. And this is a vertical plate-like reinforced concrete wall. You can say like that. A deep cantilever beam. You can say also like that a wall. A really wide column. This is like a definitions of shear wall, something like that. So this is not that very simple definition. Generally, it starts at foundation and it goes through the building height. It goes through the building height and gives stiffness. Of course, it gives stiffness to the building. And this wall actually get the horizontal force through the diaphragm that you have in the building, the slab system you have. And through the slab system, actually when you apply horizontal load, to the building, it goes to the diaphragm walls. Then from the diaphragm walls, it comes to the shear wall, and finally goes to the foundation. So diaphragm is
স্যার আপনার স্লাইড চেঞ্জ হচ্ছে না স্যার এখন আমাদের ফার্স্ট স্লাইড দেখাচ্ছে
ও তাই চেঞ্জ হচ্ছে না এখন দেখতেছো
না স্যার এখন আসেন
এখন দেখা যাচ্ছে স্লাইড এমনি
না স্যার এখন কিছু
এখন দেখা যাচ্ছে
জি স্যার আসছে
এখন চেঞ্জ হচ্ছে
এখন স্যার এই যে ফ্লেক্সিবল ডায়াফ্রাম রিজিড ডায়াফ্রাম
so normally shear wall you can see that it takes the gets the loads of horizontal forces through the diaphragm wall. Diaphragm is nothing but your slab. Actually, you have the slab in the buildings, and from the buildings, this diaphragm actually collect the horizontal force comes to the diaphragm and goes to the shear wall, something like that. So it can be flexible diaphragm. You may have rigid or semi-rigid diaphragm. Flexible means you will allow the deformation like this. You can see the deformation of the slab will deform under the load when you apply the load. And rigid diaphragm means your slab will not goes the deformation during the transferring of the load. From diaphragm to shear wall, if we see that how you transfer the load, of course, you apply the wind load or earthquake load, horizontal loads, and your slab, through the slab, it will goes to the shear wall. You may have the collector beams to go or directly to the shear wall, whatever it is. And during this transfer, of course, you can have this kind of compression cord here, and also here you may have the tension cord. So you need the rigidity also between these two elements also here. And I think this is the load transfer. You can get it from the books, standard.
Slide আবার start দেন।
এখনো কি দেখা যাচ্ছে না?
স্যার এখনো স্যার ইয়েটা ওই যে ফ্লেক্সিবল
স্লাইডটা
টাইপের
চেঞ্জ
স্লাইড
হয়
দেওয়া
না স্যার, একটা স্লাইড
চেঞ্জ হচ্ছে না, আমার এখানে তো চেঞ্জ হচ্ছে, আমি তো বুঝতেছি না। হারুন,
স্যার আমি তো স্যার সব অপশন অন করে রাখছি স্যার, এখন কেন হচ্ছে এটা তো বুঝতেছি না স্যার।
আমি তো এই প্রথম দেখলাম স্লাইড একটা চেঞ্জ হবে একটা চেঞ্জ হবে না, এখন হচ্ছে?
না স্যার, এখনো স্যার শুধু একটা ওই ডায়াফ্রাম, ফ্লেক্সিবল ডায়াফ্রাম, রিজিড ডায়াফ্রাম, সেমি রিজিড, এটাতেই আছে স্যার। আপনাকে স্যার হোস্টও করে দিছি, এরপরও কেন এরকম হচ্ছে?
আমি আমি একবার লিভ করে আবার জয়েন করি মনে হয়।
জি স্যার, জি স্যার।
আমি লিভ করলে কি আবার সমস্যা হবে? আমি যে হোস্ট আবার।
স্যার আমি আবার আপনাকে হোস্ট করে দিব স্যার, সমস্যা নেই, আমরা হোস্ট আছি স্যার এখানে আরো দুইজন।
এখন দেখা যাচ্ছে? হ্যালো,
জি স্যার,
এখন দেখা যাচ্ছে?
জি স্যার দেখা যায়।
চেঞ্জ হচ্ছে নাকি?
না স্যার একটা স্লাইডে দেখাচ্ছে, চেঞ্জ হচ্ছে না।
চেঞ্জ হয় না স্লাইড?
না স্যার চেঞ্জ হচ্ছে না।
I don't know. Why?
স্যার এখন চেঞ্জ হচ্ছে স্যার এখন।
এখন হচ্ছে?
জি স্যার, এখন হয়েছিল স্যার চেঞ্জ স্যার, এখন আবার স্টাক হয়ে গেছে স্যার, একটু আগে হচ্ছিল।
স্যার ওই ইয়েটা স্লাইড শো না করে স্যার এমনি দেখাইলে মনে হয় ভালো আছে, তখন একটু চেঞ্জ হয় আর কি।
এরকম হলো কেন?
স্যার ফুল স্ক্রিন শেয়ার দিলে মনে হয় ব্যাপারটা ঠিক হয়ে যেত স্যার। আপনি মনে হয় নির্দিষ্ট ট্যাব শেয়ার দিয়ে রাখছেন।
screen. এখনো একই রকম?
স্যার ইয়েতে স্লাইড শো দিলে আর কি মানে কিছু হয় না স্যার, এমনিতে নরমাল।
যাক, এখন দেখতে পারতেছো তো না এমনি?
জি স্যার, এখন চেঞ্জ হচ্ছে স্যার।
জি স্যার, আপনি স্যার এইভাবেই যেটা দিলে ভালো হবে স্যার। আপনার স্যার দেখাও যাচ্ছে, চেঞ্জ হচ্ছে স্যার। জি স্যার, দেখা যাচ্ছে স্যার।
দেখা যাচ্ছে না?
জি স্যার।
So if we see the load transfer, for example, when we apply seismic force, you can see the seismic forces concentrated at the roof and flow diaphragm. Okay, then you will have the compression cord. You understand the tension cord here, and you will have the transfer of the shear force. You can see here. আমার মাউস কি দেখা যায়?
জি স্যার, যাই স্যার, কার্সর দেখা যায় স্যার।
And finally, it comes to the shear wall. It is your shear wall, and it comes to the shear wall. And from shear wall, you goes to the foundation. So this is the way how you transfer the loads, horizontal loads, from the diaphragm wall to the shear wall, and finally to the foundation. This is very simple. I think you can easily understand that, but here is some definition, like this is the height of the shear wall, HW. This is the shear wall, and this is the height of the shear wall, and length of the shear wall, and the thickness of the shear wall is H, small h, and length of the shear wall, this is the section, length of the shear wall is LW. So this is the notation we used here for discussion. And when HW by LW, or when your length of height of the shear wall is less than 2 times of the length of the wall, we call it very short shear wall. Shear will be mainly governed here in this type. And when it becomes more than 3, you may see the flexural action in that case. And when it is 2 to 3, you may have the combined action of flexural and shear. I checked with BNBC 2020. In BNBC 2020, they defined that if your LW by H is more than 2.5, then we call it wall system like that. That will become shear wall. If your thickness is length is 2.5 times of the thickness, then it becomes the wall like that. But anyway, you can see the different definition in different cases. Types of shear wall: if you may have the rectangular or linear shear wall, you can have the flange shear wall, core wall, couple shear wall, frame shear wall, or infill masonry wall. So this kind of shear wall you can see. This is the coupled wall. You can see the two walls are coupled with the hinges of beams at the both end. So you don't have here the only the movement, individual movement from the frame is coming actually here. And you can see if you can have the also stiff couple beams, and you may make the wall the connectors with that can take the shear force and also the movement, something like the couple using the coupling beams. This is the squat shear wall. If you have very low height of the shear wall, then normally you may need to do analysis by using tie strut model during analysis, and of course shear will be governed here. And if your height is large, then you can consider it as a slender type of shear wall. You will have the, of course, the moment flexural behavior will be the controlling factor here. Here I show you some experimental data when you have the height is very low. So you can, when you apply the cyclic loading on the strut wall or short wall, you can see that the failure is mainly due to the shear cracks. So you can see the shear cracks that makes 45 degree almost with the axis, vertical axis, and you can see the lot of cracks due to the shear governed cracks. But our cases mostly, I think we will have failure mechanism like type C type of failure. That is the failure by concrete crushing here. You will have a lot of flexural cracks due to the shear force and moment. Flexural cracks due to the moment, huge moment, and you also the shear cracks also can be developed, uh, transferred to the shear cracks. You can have the large crack due to the fracture of steel at the foundation level like that. So this is the actually the way how your shear wall will get stressed. So you understand that to control these cracks under the load, we need to give reinforcement so that our walls will not fail during the loadings. So that's why, of course, you need the flexural reinforcement. You need to control the shear cracks. You need the shear reinforcement at the both faces of the walls. We have lateral force resisting structural system. You may know it that moment resisting frame. You have only the frame take the vertical load as well as horizontal load. You may have the bearing wall system only. Your wall take the loads, all loads, horizontal load as well as vertical load. You can have the dual system. Dual system, your frame take the horizontal load, and also your shear wall take the horizontal load. Also the vertical load is also taken by the shear wall and the frame system. But in the case of dual system, at least 25% of the horizontal load is to be taken by the frame system. That is one of the one of the requirement in the case of dual system. In the case of buildings frame system, actually both work separately. Like your frame system will take the vertical load, and your shear wall will take the horizontal load. Mostly in our cases, we try to design with the dual system. That is, we allow that frame system will take the horizontal load some part, and also the shear wall will take the horizontal load as well. So bearing wall system are used for apartment buildings. That is, you don't have any frame here, and also the hotels. Maybe we can use bearing wall system. Moment resisting frame system we can use for mostly, you know, that many of our buildings we use the moment resisting frame buildings, and we can have 8 to 10 storied buildings by using moment resisting frames. And moment resisting frame can resist the shear force, you know, that through the rigid joints, beam column joints, they can resist the shear force of the that will come to the structure. Then it can be ordinary moment resisting frame system. You all, I think you may know it. And also it can be intermediate moment resisting frame system. It can be special moment resisting frame system. That is the ductility requirement of the frames. If you need very high seismic zone in Bangladesh, of course you have to use seismic special moment resisting frame system. That is the seismic design category D. intermediate moment resisting frame system. You can have the special moment resisting frame or intermediate or some seismic design category D, something like that. Anyway, that is the requirement for your ductility requirement. Based on the ductility requirement, we can use ordinary moment resisting frame or intermediate moment resisting frame or special moment resisting frame. This is the another topic. Maybe you can read the BNBC and you can get some idea of it. Dual system or shear wall frames building system. This is very good system. I believe that, and we can use for even 8 to 30-story building for using this dual system. Actually, shear wall, how how it acts. If you have a short wall, you can see that if you apply load, you will have largely shear deformation. And because you can see the deformation here, and this will mostly shear type of deformation. If you have a cantilever action, you can see that you will have the flexural plus shear deformation. If I see this slide, at the bottom, you will have the large deformation, but smaller flexural deformation, large shear deformation. At the bottom, you will have the large shear deformation, but you will have the smaller flexural deformation. You can see that you will have the large shear deformation, but you will have a very small, because of the cantilever action, you will have the very small shear deformation. On the other hand, at the top, you will have the large flexural deformation, but you will have the smaller shear deformation. So if you combine these two structure together, actually what will happen that this shear deformation will be controlled by this flexural deformation, because it will not allow this large deformation. And at the top, your flexural deformation will be controlled of the wall will be controlled by this shear deformation. Yeah, I think it will be easier for you to understand here if you see the shear wall behavior and frame behavior. So if you see at the bottom that because of the shear wall behavior, you have very small deformation. But if you see the frame behavior, you will have the large deformation here. So if you combine these two, actually the total deformation will be reduced. So what happened, actually, you have the frame here, you can see the frame, and you have the shear wall here. If you add these together, actually what happened here at the top and the bottom, you can see that your shear wall will control the deformation of the frame. So this is neutralized. Actually, this will just push and pull will happen here at the top, at the and also the bottom. And when you come to the top, you will see that your frame, when you have the shear wall action, you have the large deformation, but that will be pulled by the frame system. So you can see that through this interaction, actually your total deformation among finally the moment at the base will be reduced significantly. That is the dual system. You can understand that in the case of dual system, you need to have your frame system more little bit stronger also in the case of dual system to get this benefit. And finally, if you combine your shear wall with the moment frame system, then you will have this kind of mechanism. You will have push and pull here at the bottom and at the top, and to control your overall deformation of the structure. So this is very important. If you have very weak frame system, maybe you cannot achieve this. So you need to have a good framing system also to get this benefit. So frames deform predominantly in shear mode, and source of deformation of lateral resistance is the rigidity of the beam column slab joints that we already talked that in the case of moment frame you need to have good beam column joint system to resist the horizontal load, something like that. The shear wall deform essentially in bending mode. You have seen that shear wall essentially deform in bending mode. Shear deformation are rarely significant. Low weight to height ratio is failed by shear. Behave mostly like a slender cantilever designed to resist the combined effect of axial force, bending moment, and shear. The linear sway of the moment frame, when combined with story sway of shear wall, results in enhanced stiffness because the wall is restricted by the frame in upper floor, while at the lower levels the frame restrained by the wall. That I already we already discussed, resulting in deflected shape in the form of a lazy S curve. So this is very important. You can have this important lazy S curve. To get it, you need the combined action of shear wall as well as your frame system. Shear wall frame building, of course, you can have the frame system and you can have the shear wall together, and you may need hinge at the hinged, or you may not hinge at the during the coupling beams like that. When you have the shear wall actually and frame action together, you will have a force. You can see that at the top that will resist actually the frame will resist the deflection of the wall, the flagellal deflection of the shear wall system, and finally your shear force will follow this diagram. And if you have a very flexible frame system, then you can have normal shear distribution like that. And finally your movement, if you have the very flexible system, you will have the very large movement at the base of the shear wall. You can see here very large movement, but you will reduce the movement if your frame system is stiffer. So because you have seen that when you have the frame system, a very good frame system here, this frame system actually will control these horizontal forces by interactions. So they will reduce the moment and also the deformation of the buildings. So this is actually a win-win situation. I will shortly write here that a win-win situation. You need to have very good shear wall with a frame system, more or less rigid, or some one not very flexible frame system. And if you can do that, then you can control your total deformation of the structure. That I say like that it's a win-win situation. Like shear wall will help, like frame system will help to take the lateral forces that will come to the structure. Shear wall, actually we can understand the shear wall is like it will take the shear force, actually not like that. You have seen that shear wall also take a lot of movements. You have seen that, but it by name it we may realize that shear wall means it will govern primarily by shear force, but of course it take a lot of movement. If we see the some cases of investigation, say we consider 10, 20, and 30-story buildings with and without shear wall, then how the deformation of the structure changes, we will try to show you. For example, this is a 10-story wall, 10-story wall without any frame. Wall thickness is 15 centimeter. I just copied from the slides of, that I acknowledge from their resources. And if we consider the frame system wall thickness, you will have the um, uh, only wall you have 26.73 centimeter of deformation at the top of the wall. And if we see the 10-story frame system, if you consider the frame system, then you will have the 15.97 centimeter. So you understand that when shear wall deform, actually you have the large deformation alone 26.73. When frame deform, you have 15.97 centimeter at the top. And when you combine these together, your shear wall and the frame system together, you can see miraculously, very important to note that your deformation reduced to 5.14 centimeters. So this is the actually how your shear wall and frame together, when they combine, they help reduction of the deflection. You can easily understand from here. Then they change to 20-story wall and shear wall, and you have deformation 158 centimeter, very large deformation. You have 20-story frame, your deformation is 27.35 centimeter, and here is 158. You see that. So alone, if you use shear wall alone, actually you need it will be very difficult to control the deflection. You need the both system together to control it. And if you combine both system together, you can see that your deformation, top deformation, deflection become 12.66 centimeter. So you easily realize the effectiveness of using the shear wall and frame system together. Then if you change to 30-story wall and 30-story frame, so if you have a 30-story wall, your deformation is 355. 30-story frame, your deformation is 40.79 centimeter. But of course, in the case of shear wall, because of the flexural action, you have very large deformation, but the frame will deform only 40.79. And if you combine together, your deformation will become 20.87. So the combined action of your shear wall and frame is very important. That's why your frame need to take some shear force, because if shear is frame is very weak, maybe you cannot, frame system is very weak, maybe you cannot get that benefit from the from that we are talking. That's why we need to have, in the case of dual system, you need to have stronger frame system also. So if I summarize here, you can see that if you have a wall deform a lot, shear wall, and frame system, this is the frame system, green color, and the red color is the combine action. So what we understood that we need to have the combined system, shear wall and frame system together to get the large benefit to control the deflection of the structure. They tried to calculate the stiffness of the structure using the total force divided by deformation, and they calculated that stiffness for the 30-storied cases 4.9, say stiffness for the wall 0.56 at kip per centimeter, stiffness for frame and wall 15.79. So you can see that stiffness of the frame and stiffness of the wall, this is only 5.46 if you add to, but your stiffness of the frame and wall becomes very large. So this is not like that linear combination, like that. Stiffness of the frame system individually plus stiffness of the wall system is not equal to stiffness of the frame plus wall. So your stiffness is very large. If you add these two together, your total stiffness becomes 15.79. But if you linearly add, of course, it is only 5.46. So we cannot get the we cannot add the stiffness together. You can see from here. Of course, to get that, you frame system need to be stronger also in to couple with the shear wall system. And if we have see the moment, not only the deflection, but if we see the moment also, shear wall moments, if you don't use the free cantilever, if you have the free shear wall, you have the very large moment. But if you have the frame interaction, shear wall frame interaction with and without slab, with slab, or with beam and slab, something like that, you can reduce your moment at the base almost 3 times. You can see here almost 3 times you can reduce if you have the interaction with the shear wall and the frame system. So we can easily understood that shear wall and frame system need to act together to control not deflection as well as to reduce the moment at the base. And this of course happened due to that I explained earlier, that you interaction between the shear wall and the frame system, because the shear in the case of shear wall will not allow the deformation at the base level, and the frame will control the deformation at the top of the buildings. So both will actually interact each other together and will control the deflection and moment of the structure. This is very important slide. I believe that the Khan Brownies curve I just copied from the internet. Uh, this is very, I will say that this is very important. You can see that if you have the free wall deflection, that is you don't have frame system, you don't have frame, then you deflection of the structure divided by free deflection of the shear wall at the top, you can see this is very large. But if you increase the stiffness of the frame system, that is that you reduce the SSSC lower level, then if you increase the stiffness of the frame system, then you can see the benefit of the deflection that we also explained in some buildings, 10, 20, and 30-story buildings. This is I believe that almost similar. So your existence interaction of frame system is very much essential actually to control the deflections. Wall frame interaction key conclusion: the shear wall deform predominantly in bending mode. The common assumption to neglect the frames in lateral load resistance can lead to grossly anomalous results. The common assumption to neglect the frames in lateral load resistance. You understand, I believe that. So you have seen that shear wall and frame need to work together. If frame cannot help to control the deflection, then how you will control the deflection of the structure? So you need to have good interaction between your shear wall and the moment resisting frame system. Consideration of shear wall frame interaction lead to a more economic design. I think it is very important. The shear wall should be designed to resist the combined effect of axial bending and shear. Layout of the shear wall in plane is very important both for vertical as well as gravity load. So this is you know the locations and other shear wall is also very important. Reinforcement in shear wall. Now come to the reinforcement in shear wall. We can have the shear wall with the boundary element. This picture, this is the boundary element actually. You have the end of the, you know that you will have the large movement at the edges, large bending stress at the edges of the wall. So you will have the boundary element here, but you don't need no boundary element. You can have the walls without the boundary element. Just 1 minute. lot of noise coming. Then you can have the flanged section, like you have the wave flange like that. So you can have the, when you have the very large movement, of course, you need to have provide the boundary elements to take the over stress. And if your stress is more than 0.2 of f prime c at the boundary level or edges of the shear wall, then you need to provide some additional section to control the compression in your concrete. So that's why you need the boundary element. So the thing is, you may give the uniform reinforcement, you may give the design shear wall with the boundary element with flange section, or you can use the some reinforcement. You don't change the section, but you give some additional reinforcement in the boundary edges, something like that. Critical section of a shear wall for both flexural and shear design. Normally, we consider the critical section, that is the height of the wall divided by 2, length of the wall divided by 2, and the story height. But we need to use the minimum value for moment and shear, something like this. This is the critical section. I think we'll have one problem and we'll discuss it during solution. A shear wall of a building may subject to a variable shear, of course, which reaches a maximum at the base. Of course, if you analyze, you can easily find that it is a very low shear force at the top, and when you come to the down, so you have to take all of the shear, and finally at the base you have the large shear force. So you may have the triangular distribution, something like that, or parabolic distribution, whatever it is, or you can apply the, anyway, you can do the analysis and you can apply on the structure. A bending moment which tends to cause vertical tension near the loaded edge and compression at the far edge. So this is very simple. If you have a cantilever, if you apply the horizontal load, the loaded face will be in tension, the other edge will be in compression due to the movement. You know it also, I believe that. A vertical compression due to the ordinary gravity loading from the structure. This is very important, that in the case of cantilever beam, we may not have a very strong axial force in the system, but in the case of shear wall, it is not like that. You have a very large compression also, because the shear wall can take a lot of compression also, a lot of vertical loads also will come here, and it will increase your shear resistance capacity of the concrete. And whenever we design a structure, you already know that nominal moment, if you calculate the nominal moment, and if you multiply it with the capacity reduction 5 factor, then this you get the capacity of the your section, and of course it should be greater than your design or the moment shear axial force that you get from the factored load from your analysis. So your capacity of the section, of course, should be greater than your required moment, required shear force, and required normal force. Normally, you have seen this equation. I believe that when we talked about the reinforced concrete design classes, we already talked it. Minimum shear reinforcement. Can you see this slide? Hello.
জি স্যার দেখা যায়।
স্যার লেখাগুলো অনেক ছোট স্যার। You can see the slide, but
এখন আমি একটু বড় করে দিয়েছি, দেখা যাচ্ছে?
the writings are very small.
দেখা যাচ্ছে এমনি?
বড় হয় না স্যার, এমনি ছোটই আছে আর কি।
ছোটই আছে না? আচ্ছা, যাই হোক, এখানে ওয়ালে আমরা we know it that the minimum amount of shear reinforcement, that is 0.25%. This is as longitudinal as well as is a transverse direction. You need to provide minimum shear reinforcement of 0.25% of the gross section in the both faces total. You transverse reinforcement and your longitudinal length reinforcement both should be minimum 0.25%. And spacing of the horizontal shear reinforcement shall not exceed length of the wall by 5 or 3 times of the thickness of the wall or 18 inches. And in the case of longitudinal shear reinforcement, it becomes length of the wall by three times of the shear wall thickness or 18 inch. So we have to satisfy, actually we'll discuss this later also, so you will get it. This is the minimum requirement for your shear reinforcement, spacing of the shear reinforcement. Can you see now? Hello.
जी सर देख
We need vertical flexural reinforcement, we need horizontal shear reinforcement, we need vertical shear reinforcement. So we need a lot of reinforcement. You can see that horizontal shear reinforcement, vertical shear reinforcement. I explained one of the slides with the shear cracks and the flexural cracks. You can at the beginning of the presentation. Actually, to control that cracks, you need horizontal shear reinforcement, you need vertical shear reinforcement. And of course, to develop the moment, you need the vertical flexural reinforcement with or without a boundary boundary element, something like that. And how much shear force will be taken by the shear wall? If this is very similar to the equation that we used for calculation of the beam shear. If you can remember, this lambda is equal to actually the light weight factor. This will be 1 if you use the normal concrete. I think you can remember 2 square root over f prime c. Phi is not here. Phi is will be used later, so phi is also will be here. And to root over f prime c, h is the thickness of the wall, and d equal to you the effective depth of the wall, something like that. So you can calculate how much shear force can be taken by the concrete. We can easily calculate. This is same as beam, I think, if you recall. And if you have the axial tension in the beam, of course, you need to normally in the case of beam, we don't consider axial forces a lot. You can still remember, I believe that. But of course, beam can be subjected to axial force, tension, or compression. If it is subjected to axial tension, you need to reduce the capacity of the shear capacity of the beam. So that in that case, you have to use this equation. You have to use NU, that is you calculated the axial tension from the factored load divided by 500 divided by AZ. The AZ is the gross area, something like that. And this NU will be negative actually because this will be tension here. So it will be negative. So it will be lower than 2 lambda root over f prime c HD or BD, something like that. So if you have a tension in the shear wall, actually you are reducing the shear capacity of your concrete section that you provide for the shear wall. And this is also same as beam. You could not have the 10 root over f prime c HD if your shear force is like that. That it is very difficult to control. So you need to change the section if you nominal shear crosses or and from analyze if it crosses 10 root over f prime c HD, you need to change the section, something like that. And to calculate D, you can consider 0.8 times of length of the wall, something. So if you want to calculate the D effective depth, you just use 0.8 times of length of the wall. This is the LW, something like that. So you can easily get the effective depth of the beam. And if we have the axial compression, of course, if you have the axial compression, it will help you to increase the shear capacity of the section. And finally, you can use this equation, equation 1843 or equation 1844. And of course, the minimum value you need to use based on these two equations. What is the minimum value you get? That can be the shear taken by the concrete under the compression, axial compression. So this is the axial tension, how you do the calculation, and this is the axial compression, how you get the shear capacity of the section. When the factored shear force BU does not exceed BC by 2, AY may be a wall may be reinforced according to the minimum reinforcement. So you know the minimum reinforcement that I explained you, that is written once again here. Minimum transverse reinforcement ratio, that is 0.0025, and spacing is LW by 5, 3 times of slab thickness or 18 inches. So you have to use the minimum value, the spacing. You can easily calculate it. And for the case of vertical reinforcement, you need to use this equation. If rho t equal to 0.0025, so you know that longitudinal, this will be cancelled out and it will be 0.0025, something like that. And the spacing will be length of the wall by 3 times of the slab thickness or 18 inches, something like that. So you can, I think you can easily calculate what will be the transverse reinforcement and what will be the longitudinal reinforcement from these equations. And the last two equations, I think you can remember the shear design equation. This is nothing but the equation that we use to calculate the shear reinforcement that we already derived in, I think, when I talked about the shear design of reinforcement. I think we already talked it, so you can calculate amount of the shear reinforcement from these equations. And finally, of course, you need to satisfy, you have concrete, you have steel, and your nominal shear will be taken by concrete as well as steel. And of course, your design shear force should be more than your required your shear force that you get from the analysis, something like that. And shear reinforcement calculation, you can have these once again, it will be 0.8 LW, LW. This is the D actually, and it should be lower than 10 times of this values. I found one of the other slide, the minimum reinforcement for walls in plane with if 0.55 root over 5 VC, if the shear force is very small, and you can also use less amount of reinforcement, like minimum longitudinal reinforcement and minimum transverse reinforcement. They have also provision for less reinforcement. Instead of 0.25, they can they suggest to use 0.12% or 0.15% also, based on the strength of your reinforcement. That is also, that provision also I have found in ACI 31890. So if shear force is very small, maybe we can reduce the amount of the shear reinforcement to 0.15% around. Designed for flexure, we can have the uniform vertical reinforcement without no boundary elements. Of course, if moment is less, we can use this kind of section. Of course, this vertical shear reinforcement will take the flexural moment. This will give you some flexural moment resistance. And how we do it? This is the section you can see here. This is your section of the wall, and this is your moment. This is your axial force is coming here, and this is LW, length of the shear wall, and uniform reinforcement here, no boundary zone here. And this is the due to this moment, you have the tension here, little bit tension, and you have the compression at this phase, and you can see the strain distribution. This is the strain distribution here. And what is CC is the actually depth of the compression block of your wall. This is the compression block of the wall, and your reinforcement is strain in tension zone is more than 0.005. Actually, we have some assumption here, like all steel in tension zone yields in tension, all is still in compression zone yields in compression. So this is your tension zone and this is your compression zone. You assume that you both still in tension and compression will yield something like that. The tension force acts at the mid depth of the tension zone. That is, this is the tension zone, and your tension force, actually this tension force will act, this is the tension force, internal force that will act at the mid depth of the tension zone, you can see here. And this compression also will act at the mid depth of the compression zone. The total compression for some of the steel and concrete together acts at the mid depth of the compression. So you don't consider the separately the compression from the concrete here. You assume that total compression will act at the mid depth of the compression zone, and total tension will act at the mid depth of the tension zone. So if you, this is your depth of the compression block. If you do some simplification, you will get that the tension force just come from the steel and to the neutral, to the mid section, the distance will be C over 2. This will become C over 2. And compression to the center line of your section will be LW, length of the wall, minus C divided by 2. So if you do the some simplification, you can easily get it. And I'm sorry, it's very difficult.
Sir,
So
if you
what
want,
will
we
be the
can take a
amount
break,
of
sir.
tension? No, it's okay. Maybe I'm far, a little bit more than. How we can get the tension in steel, that is AST is the total steel. AST is the total area of the longitudinal steel. You can see here, AST is the total amount of the longitudinal steel. So if I multiplied it with the FY, I get the total force coming from the longitudinal steel, is not it? Then if I divide it by LW, so I can get the amount of the force coming from the per unit length of the wall, something like that. Then if I multiply that by LW minus C, actually I get the amount of the force coming from the tension tube, something like that. That's why you can see here that AST into Fy, this is the total tension force of the section if the all steel are yield. And if I divide by LW, that is I get the per unit length of the wall, the force, then I multiply it with the LW minus C. LW minus C is the length of the tension zone. So the total amount of the force that is coming in the tension zone, that is nothing but we can write by this equation. I think you get it maybe. And total amount of the compression in steel, that is similarly AST into Fy, you divide it by LW, so you get the per unit length, then you multiply it by the C. C is the length of the compression block, then you get the force coming from the steel of the compression block. Then CC we can get it from Whitney's stress block, you can remember that 0.85 F prime C, that is the average stress, S into C into beta 1. So beta 1 is the uh, stress here, you know, the term of the beta 1, and then finally total compression, we can get compression in steel as well as compression in concrete. So these are the equation I think you easily develop for this. The percentage of total longitudinal reinforcement is AST is equal to total amount of the steel you have in the section, longitudinal steel you have in the section, divided by H LW, that is the percentage of longitudinal steel. Of course, this should be more than 0.25%. You already know that. And longitudinal reinforcement index, there are two parameters here. They have like that longitudinal reinforcement index omega rho L, this into Fy divided by FOMC. And also the stress parameter one, alpha equal to Nu divided by HLW FMC. Nu represent the factor axial load, and this will be positive in compression and negative in tension, something like that. And finally, you have the equilibrium equation. Your compression or tension should be in equilibrium, or you can write external axial force equal to internal axial force, whatever it is. You know it very easily. You can develop it, and you already know what is CC, what is CS, what is T, that I explained here. You already have these forces. Then you can write it here, and finally you can simplify it here, and you can solve for C, and you can get the C is like that. So C is alpha plus omega 0.85 beta 1 plus 2 omega into LW. So this is C is nothing but your compression, depth of the compression zone, something like that. So you can easily get the depth of the compression zone using this equation. And if you know the depth of the compression zone, you can get the nominal moment capacity of the section, that if you take the moment LW Mn T into LW by 2 Nu, you take the moment actually here in just one minute from the then the summing the moment about the compression force. So you take moment here at location C. So you will have the Mn and then the Nu LW minus C divided by 2. This is the moment term. So you have this term, and also you have the this one T is coming from the tension steel, and the moment term is LW by 2. So you have this moment term LW by 2. If you take moment center, the equation will be different, of course. We take here moment along the compression along the at C, the compression force along the compression force. We take the moment, and finally we have these equations. And you can have the load cases like 0.9 D dead load and 1 wind load, 0.9 D or 1 earthquake load. Of course, if you have the service load factors, government use a load factor. You can use the, if you use the service level wind forces here, so you have to use 1.6 of wind load, something like that. So to have the to over stress the section, you can use 1.6 times of that. And when you have the compression control, actually we have the tension control failure, we can have the compression control failure. And normally we want to have the tension control failure, you know that. And in the case of tension control failure, normally the reduction factor phi equal to 0.9. And when it will will be happen like that. If I write the section here 0.003 0.005, you can see here I can write this compatibility equation C by 0.003 divided by D minus C divided by 0.005, and then I will get C equal to 0.375 D. So if your compression zone is increased, actually, if compression zone is increased, then your failure will be it will be compression control. That time you can use phi factor equal to 0.65. But most of the cases you may get that you control the tension control. That is the you will have the large deformation through the tension controlling of the steel bar, and then you will have phi factor equal to 0.9, something like that. We may need the boundary element. I already explained you that you need to use the concentrated vertical reinforcement for taking the moment. And for that, you need to tie also the boundary elements should be tied also together through the reinforcement. That is also very essential. So that we will have one example with the boundary element and one example with the without the boundary element. You may have the boundary element within the wall without changing the section that I already explained you. A wall with a large boundary element, you can have the boundary element like that. So you can see that boundary reinforcement also, you use the tied reinforcement in the boundary. You can have the flange in flange form uh, in the boundary also. So this is the common type of shear wall you have. The confinement requirement are more stringent for boundary elements of structure wall in region of high seismic in region of high seismic zone. So this is, you have to use seismic design category D, and you have to follow the seismic detailing also in that case. The contribution from vertical reinforcement in the wave is usually ignored because its contribution is quite small compared to the contribution from the vertical reinforcement concentrated at the edges of the walls. So in the case of if you have the boundary element, normally your movement will be the boundary element. Can you give 5 minutes break? Hello,
Yes, sir. No problem, sir. We can have a 5 minute break.
জি স্যার ভাই
just 5 minutes. 5 minutes.
ওকে, 11:17 ঠিক আছে, 11:17-18 আবার শুরু হচ্ছে।
11:07 Hello.
जी sir.
Let's see one example. I just copied from a book. Actually, this example, I think this book from the Ferguson maybe. Anyway, I will also give you the notes at the end of the session, so you can go through the books also. Um, can you see the now presentation slides? Hello, is it moving?
না স্যার এটা স্লাইড শোটা মানে দিলে কাজ করে না।
I don't know. Anyway, let's see. Let's see, no problem. So this is one review example. You have building shear wall like this, 12 feet at the bottom. Floor then 10.5, 10.5, 10.5. This is a 5-street shear wall, something like that. You have loads, 30 kV, 50 kV vertical loads, and you have also the horizontal force. You can that's coming to the structure, something like that. And I have shown you the critical height. It will be LW by 2, that is the 9 feet, that is the minimum. So that is the critical section actually for checking the shear force and moment here, like that. And the section is provided, you can see number 4 bar at the rate of 16 in center to center, and also number 5 bar at the rate of 18 in center to center. That is the vertical reverse. Number 5 bar at the rate of 18 in center to center, and horizontal shear reinforcement. Number 4 bar at the rate of 16 in center to center. Your concrete strength is 4,000 and your FY is 60,000. Consider normal weight concrete, that is an lambda equal to 1, something like that. So first we'll see that whether the shear reinforcement is enough or not. First to say longitudinal reinforcement. This is the longitudinal reinforcement, area of AB horizontal. I think this horizontal reinforcement. Yes, sorry, this is the horizontal reinforcement, first one, horizontal reinforcement. So AB horizontal reinforcement, you have, if you see here, horizontal number 4 bar at the rate of 16 in center to center. That is, you have 0.2 inches square into 2, because you have 2 leg ties, horizontal reinforcement. So you multiply it is by 2, that is the AB horizontal, divided by H into H2, that is the spacing of the reinforcement, 10 into 16 inch. So this give you the percentage, actually percentage of the longitudinal steel, that is 0.0025, that is satisfy the minimum requirement. And your spacing is LW by 5, 18 inch or 3 inch. So you have minimum spacing is will be 18 inch. But you are using I think very number 4 bar at the rate of 16 in center to center. So that is also okay, no? Yeah, this is here, no? 16 in center to center. So this, you satisfy the requirement. Then you come to the vertical reinforcement. You have vertical reinforcement, if you see here, number 5 bar at the rate of 18 in center to center. So number 5 bar means you have 0.31 inches square reinforcement. You have 2 faces here and here, both faces you have reinforcement. So you multiply it by 2 into 0.31, then you have the section spacing into your depth, that is your 10 is your depth of the section H thickness, and 18 is center to center. You are giving 0.0034, and that is also more than 0.0025. So you satisfy this requirement, and this is the minimum spacing, LW by 3, 18 inch or 3H, and you will have 18 inch, but you also give, I think, 18 inch center to center, something like that here. Number 5 bar 18 inch center to center. So So this is satisfy your minimum requirement. This is the check for wall reinforcement, minimum reinforcement. Then check for flagellal strength. We use the possible critical load 0.9D plus 1.6 times of the live load. We add horizontal load, something like that. So they have the total moment at the base 2.9. You can calculate moment what will come actually from the horizontal loads. You can get it very easily, I believe. So you will have 2910 key feet, and as the factored moment at base, you multiply it by with 1.6, 1.6. So you will have 4660 key feet of movement. Factored axial load at the base reduce. You will have 207 kif. If you add all together, you will have 250, 50, 50, 200, 230. So you will have 213 to 0.9207 kips. And you have the beta one for this concrete 4000 psi. You know it already. You can get the omega factor rho L F Y divided by F prime C. You will get it. You can get the alpha factor. You know everything. You can get it. Then you can get the depth of the compression block. You have this equation. We already discussed it. So you will have 19.8 inch of the depth of the compression block, and your 0.375D is which is less than 0.375D. So D equal to 0.8 of length of the wall, and it is smaller than that. So this is tension controlled, and you can use phi equal to 0.9. So that is the moment control, something like that. You will have phi equal to 0.9. Next, we will calculate the value of AST, how much steel we are providing in the longitudinal longitudinal steel, how much total longitudinal steel. That is 2 into AB into LW divided by S1. This is actually number of steel bar in one phase. You can, if you think it, LW by S1, this is the number of steel bars actually in one phase. So you multiply by 2 into AB, you get the total amount of longitudinal steel, that is 7.44 inches square. So now we can calculate the tension force that I already discussed this equation. This is the total amount of steel Fy, then Lw minus C divided by Lw. You will get the tension 405 kips from the steel in tension zone. And finally, you can calculate the moment, moment T Lw by 2 Nu divided by Lw minus C by 2. That this equation we already discussed actually. If you forget, you can come here and you can see how we get it. You can easily get it. It's not that difficult equation. So you can this moment, that is 5340 key feet, and if you use the factor 0.9, you will have 4800 key feet, but your moment is required moment is 4660 key feet. You can see from here 4660 key feet. So so the shear wall has adequate flagellal strength. That is, we don't need, of course we don't need boundary element. That also we need to check it here. Compressive stress at the bottom of the shear wall. If I use this equation, this is just a stress equation, you know that from the axial stress, from the flagellal stress, you can calculate what will be the stress at the boundary zone, and your boundary zone stress, compressive stress, comes 775 psi. You know the moment, you know the axial force, you know the moment of inertia. I just use Excel sheet and copied here. You can do it by your own, and your 0.2 FRMC becomes 800 psi, and your stress is 775. So you don't need any boundary reinforcement. because it is less than 0.2 of FMC. So boundary element is not required. Check for shear strength. Now we check whether shear strength for shear. We have checked for minimum shear strength, shear reinforcement, but we have to see whether we need the shear reinforcement or not. You have the factored shear force 120 kips, and you know the section is compression. You have seen that section is under compression, so you use the equation for related to the compression. So you have to use the minimum values from these two equations. If I go behind once again, if you have this equation here, yes, this equation is you have here. This is under compression. So you satisfy these two equation and calculate what is the shear capacity of your section. So you can find that the minimum is 2122 kif, and you have to multiply with the shear reduction factor, capacity reduction factor for shear 0.75. You have 159 kips, but your shear force is 120 kip. So you don't need actually shear reinforcement. The minimum shear reinforcement will be good enough for the section. This is, I think, earlier, if you stress at the boundary zone becomes 0.2 FMC, more than 0.2 FMC, you need to provide the boundary zones or boundary element. And if stress become 0.15 FMC from the location, if at this location it become 0.15 FMC, you can omit the boundary zone requirement for the boundary zone in the top of the shear wall, something like that. This is, I think I already explained here, this requirement for the boundary zone or boundary element, something. Next, we will talk about the if we have boundary need the boundary element, how we will design the section. Now we'll talk about that. This is the boundary zone. You can see from here. This is the boundary zone, and this is a moment is coming this direction. So you will have the tension here. You will have the compression here. This is very simple. You know that from the moment diagram, from the moment direction, you can easily identify that. Here we assume that your tension, this is your tension T. This is the coming from the boundary zone tension reinforcement. And this is the C, actually, the compression coming from the concrete. We neglect the compression reinforcement at the compression zone, something like this. So C, and this is the location of the compression. This is the, you know, that A/2. The depth of the compression block is A. You know it witness stress block, and the C will come at the A/2, something like that. And these are the distance for the T, and this is the distance from the neutral center line of the beam to the LW by 2. And of course, you can easily get T equal to S into Fy, because you know the amount of the steel here. You know how much steel you have, so you can calculate what is the T. T will be equal to S into Fy. So you can easily get it. And what is the compression in concrete? That is 0.85 FMC A into B. So A into B is nothing but the area. You can see here, this is the area into 0.85 FMC is the average uniform stress. You multiply by area, you get the compressive force. No? Then you can calculate the A. Same as we normally write ASFY divided by, you can remember 0.85. But here you have compression, so you have to add it from the equilibrium. Then you can get the value of A from this simple calculation. And if you take the moment about the compression force, once again, you take the moment about the compression force, then you can write T into D minus A by 2. This is A by 2, and T into D minus A by 2 plus NU. This is your NU LW minus LW by 2 minus A by 2, or you can write LW minus A divided by 2. So you have the moment equation of the section. So here you neglect actually the compression reinforcement. And if you have the compression control 0.375D, if you have less than these values, your depth of C, then you can use the capacity reduction factor, that is 0.9. Condition of boundary elements. Actually, I already talked to you that you need the boundary element when you have these 0.2 FRMC in the boundary zone. If it cross this value, you need the boundary reinforcement, boundary element you need. And also you need to check the other requirement for boundary element related to your deflection control. But anyway, I did not see the note I prepared. I did not have these checking for that. But if you use the software, maybe you need to check, or software may check it. This requirement also automatically, if we have need for the boundary element. You need to provide the reinforcement in the boundary element. You have to follow this minimum reinforcement for the boundary zones, and also this 400 over FY. The longitudinal reinforcement ratio at the wall boundary shall be greater than the longitudinal reinforcement in the wall should be greater than 400 by FY. This is also one of the requirement. This is for hoof ties. No? This is for hoof reinforcement. And this is for minimum reinforcement for your minimum reinforcement ratio for the longitudinal reinforcement in the boundary wall. This is the last example actually with the boundary wall, with the boundary element. This is the section you can see here, 3 inch 4 spacing at the rate of 6 inch. This is 9 inch. This is the boundary element, boundary zone here, and the thickness of the shear wall equal to 12 inch. You have 120 feet long shear wall, and this is the horizontal load coming, and this is wall LW equal to 24 feet. No? 24 feet, and you have lateral earthquake force E assigned to this wall is 205 kips. 205 kips. The dead and the reduced live load at the base of the wall is 1000 kips, and reduced live load is 450 kips. FMC equal to 4000 psi, and FY equal to 60 ksi for all reinforcement. And I think this problem structure was analyzed by Mr. From some reference you can see here. So check for moment strength at the base of the wall. If we consider the triangular distribution for assumption, so we will have that 205 horizontal load will act as over the 2/3 height. You know it. So your moment will be 16,400 kip feet. I think you can easily get it, from the just simple triangular distribution. You can easily get it. And what is the total tension force? That is AS into FY. You know it. AS equal to, we have 10 bars. If you see the section here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You have 10 bars of 12 cross bar. You have the 1 bar. I think this will be area will be number 4 hoops. Sorry, here number 10 bar, number 10 bars. Your area is 1.27 inches square for each bar. For number 9, you know that area is 1 inch square. Number 10, you have 1.27 inches square for each bar. You have 10 bars. So 10 into 1.27 into 60 KSI, you have 762 kips. So that is the total tension coming from the tension zone, reinforcement in the boundary element you give provided in the tension zone. Then you calculate the D. What is D? D equal to LW. If you come here, so this is the, you deduct here 3 and you come to the center like that. So I think you can easily get it, and this D becomes 273. The factored axial load for this load case is 0.9 D and D. Then you have the reduced dead load 900 kips. Then what is your value of the A? You can easily calculate. The A will be 40.7 inches. And what is C? C equal to A by beta 1. You already know it. The location of the neutral axis, that will be 47.9 inch, but which is less than 102 inch. That is 0.375 D. So this will be also the tension control. You can easily understand. This will be the tension control section, and you can use phi equal to 0.95 capacity reduction factor. For moment, you can use 0.9. Then finally, of course, you can get to the moment equation, T into D minus A by 2 plus NU L minus LW minus A by 2. This equation actually here you have it. This equation. So if you take moment here, we can get this equation. So finally you can have the moment. What is your moment from the design, from the use section can take, of course, use section can take 22,800 key feet. But your moment, your analysis, if you see the analysis of the moment, you will have 16,400. So you can your section is your boundary element is good enough, or your section of the shear wall is good enough to take the a lot to take the moment. Sometimes we do the capacity based design shear. That is actually if for example, my section can take this amount of moment. If before that my section failed due to the shear, actually, then I cannot ensure this amount of moment, development of this moment in the section. That's why we need to do the capacity based design shear, check for that, and we can calculate the probable axial load, that is the sum of the unfactored dead load plus unfactored reduced live load. That you can assume, they assume it in that way, and they got it 1450, and they recalculate the value of A. A becomes 54.2 inch. That is still in the tension control region, and they calculated the moment, probable moment that can be developed by the section, that is 29,700 key feet. Then they calculate the shear force that is required to develop this moment, and they consider 0.5 HW here, HW height of the wall. And finally, they found that they need 495 kips of shear force actually to develop this moment, which is much higher than 2.5 times higher than the shear force that coming to the structure. That is, the structure will never fail due to the shear. First, they will fail due to the moment, because the moment will control first, and finally it goes to the shear. So this one of the requirement, actually, capacity based design shear. Sometimes we need to you know that when you do the design for a special moment resisting frame, if you can recall that, in that case we have to ensure that we never allow the failure due to the shear before the moment. So that's why we need to check sometimes capacity based design shear, particularly for the cases with spatial moment resisting frame system, and also intermediate moment resisting frame system. I think I think that is the yes, little bit. Let's see. Come on. Then we can see the check for shear strength that I didn't check yet. So you know the section is your length of the wall is 288 inch, 12 inch your thickness. You have this section. You have the transverse reinforcement much higher than your requirement, 0.0025 for the horizontal reinforcement or transverse reinforcement. Then this is also greater than the minimum required as per the ACI code. This is also you satisfy. Then you can calculate shear capacity of the wall using this equation. You can calculate the shear capacity of the section and shear capacity nominal shear capacity. You can get the 1030, and then design shear capacity will be 773 kifs. And of course this is higher than the shear force, capacity based shear force that you have here. You have only, I think, 495 kifs. So that is also higher than your capacity of the section. So your section will not fail by the shear force before the bending failure of the section. Thus, the 12-inch thick structural wall with the indicated vertical and horizontal reinforcement has adequate moment and shear strength, and the reinforcement satisfies all of the ACI code requirements. So anyway, I plan to discuss up to this. Of course, you have to follow the seismic detailing of shear wall. I don't know. I maybe I will request you to refer to the BNBC 2020, and they have the very stringent requirement for shear reinforcement, for shear wall detailing of the reinforcement for shear wall in the case of seismic design categories, and also the requirement for special requirement for special moment frame or intermediate moment frame if you design using the shear wall. So you can refer to that. I think you have some questions. Maybe I will try to answer your questions if you did not able to understand some part of the presentation. Thank you so much. হ্যালো হারুন, শোনা যাচ্ছে?
জি স্যার, যাচ্ছে স্যার। কারো কোনো কোয়েশ্চেন থাকলে স্যারকে করতে পারো।
স্যার আমরা তো স্যার ওই যে কি বলে মোস্ট অফ দ্য টাইম স্যার আমরা দেখা যাচ্ছে রিজিড ডায়াফ্রাম ইউজ করেছি। তো স্যার এই যে ফ্লেক্সিবল ডায়াফ্রামটা আমরা মানে মানে কখন ইউজ করি স্যার? মানে
ফ্লেক্সিবল ডায়াফ্রাম তো নরমালি আমরা সাধারণত আমরা ইউজ করি না। নরমালি ইফ ইউ ইউজ দ্য ইট হ্যাভস মোস্ট অফ দ্য টাইম উই ইউজ দ্য rigid diaphragm. Of course, you can use the flexible diaphragm, and that time you depending on the stiffness of the different location of the collection system, you know that the shear force will be transferred to the shear wall system according to the stiffness of the walls. If the like that, if your slab is very soft, for example, and if you have a shear wall at that soft location, of course you cannot transfer the shear force if you have the wall at that location. Anyway, if you have that system, of course, maybe I think that your software can take care of that transferring of the shear forces in the shear wall system. But once again, most of the time we normally your slab is very highly resistant in plane, very stiff in plane. It is very stiff. So you can assume that in-plane rigid diaphragm. But if you have the steel building, I don't have that experience. I believe that steel building, if your slab thickness is very small, and maybe you may consider to think the flexible diaphragm if you go for steel building design using the deck system with very low slab thickness, something like that. বুঝতে পারছো? Hello.
জি স্যার, বুঝতে পারছি।
But mostly you use, I think, reinforced concrete building. I think you should use the rigid diaphragm. But of course, if you use the flexible diaphragm, you have the provision in the course. In the software can take care of it, and they will distribute the shear forces accordingly to the wall system.
আর স্যার কখনো যদি স্যার মানে ইয়াতে শেয়ার ওয়ালে যদি আউট অফ প্লেন বেন্ডিং কনসিডার করা লাগে তখন স্যার মানে কি কি চেঞ্জ আসতে পারে ডিজাইনে?
If you have out of plane bending in the case of the shear wall, then I think that that will reduce maybe your capacity of the section. You know that when we have a columns because of the buckling effect of the columns, if we have goes to the outer planes, then we need to have a lot of provisions there, you know, that you need to increase the moment, and also you need to analyze the second order analysis using the P delta, you know that. But I am not sure in the case of shear wall is very, you know, that in plane is very stiff. I don't know that whether you need to consider it in the case of shear wall, but in the case of column you need to consider that considering P delta analysis or second order effect, or you can magnify the moment based on your slenderness ratio.
জি স্যার, বুঝতে পারছি।
This is, I think, this is not that easy actually for shear wall. I have no experience, but I will say this is not that easy to have very out of plane bending of the shear wall. Not that easy maybe.
Any more questions? I think you guys have no more questions. I will share the video with you in your Google Classroom. Sir, আপনি কি স্লাইডটা দিয়ে দিবেন স্যার?
হ্যাঁ, স্লাইডটা আমি একটু ইয়ে করে ওদেরকে আমার কিছু নোট আছে, ওই যে মানে বইয়ের নোট, সেগুলো আমি তোমাকে দিয়ে দিব, আর কি তুমি একটু ওদের সাথে শেয়ার করিও। আর ওদেরকে এই যে প্রবলেমটা দিয়েছিলাম ওদেরকে একটু দুইটা প্রবলেমে একটু ডাইমেনশন গুলো একটু চেঞ্জ করে একটু করতে দিও আর কি। হারুন, বুঝতে পারছো?
জি স্যার, বুঝতে পারছি স্যার।
তাতে করে তাদের ওই যে রিকোয়ারমেন্ট যেটা হলো একটা হলো নলেজ যেটা আমাদের PO1, সেখান থেকে সেটা আসবে PO2 অ্যানালাইসিস, এবং PO3 যেটা ডিজাইন। হ্যাঁ
জি স্যার,
এই তিনটা জিনিস আমাদের এখান থেকে আসবে আর কি।
জি স্যার, বুঝতে পারছি স্যার।
তুমি ইচ্ছা করলে ওদেরকে একটা ছোট্ট কুইজ দিতে পারো আর কি।
জি স্যার। স্যার, ওরা ওদের যে বিল্ডিংটা
আমার
স্যার
সাথে
ডিজাইন
কথা বলে।
করতেছে স্যার, ওইখানেও স্যার ওদের ডাইমেনশন আসবে স্যার, ওদের আলাদা আলাদা গ্রুপের জন্য স্যার। ওইটা ধরেও তো স্যার ওরা ম্যাপটা হাতে করে দিতে পারবে স্যার।
হ্যাঁ, ওরা করতে পারবে। হ্যাঁ
জি স্যার, ওদেরটা আলাদা
ওরা
আলাদা
করতে
ডিজাইন
পারার
হয়েছে স্যার
কথা।
বিল্ডিং।
হ্যাঁ, ওরা
জি স্যার।
হ্যান্ড ক্যালকুলেশন করো, স্যার যেভাবে দেখাচ্ছিলাম এভাবে করতে পারার কথা আর কি।
জি স্যার, বুঝতে পারছি স্যার।
হ্যাঁ, করতে বললে ওরা সফটওয়্যারের সাথে ওরা কম্পেয়ার করতে পারবে আর কি। দে ক্যান
জি স্যার।
কম্পেয়ার উইথ দ্য
জি স্যার।
সফটওয়্যার।
জি স্যার, আমি এটাই করবো না স্যার, ওদের যে আলাদা আলাদা বিল্ডিং ডিজাইন হয়েছে ওইখানে ওরা শেয়ার বার ইনকর্পোরেট করে এটা হ্যান্ড ক্যালকুলেশন করে দেখা স্যার, সাথে ওইটা ইসে সফটওয়্যারের ভ্যালুগুলোর সাথে কম্পেয়ার করে দেখা।
তোমাদের স্টুডেন্টদের এমনি তোমাদের কাজের কি অবস্থা, মানে স্ট্রাকচারাল, কেউ যদি একটু এক্সপ্লেইন করতে একজন। হ্যালো
শাহরিয়ার, বলো তোমরা কি কি করেছো?
স্যার আমরা মেনলি ওই মডেলিংটা করছি স্যার আপাতত মানে আমাদের যে আমাদের যদি স্যার মানে বেসমেন্ট আছে, তো স্যার এটা ওই যে আমাদের গ্রাউন্ড ফ্লোরটা মানে ওখানে আমরা পার্কিং লট কনসিডার করছি স্যার। আর স্যার হচ্ছে আমাদের যে কি বল বিমে স্যার মানে আমাদের এটা রিনফোর্সমেন্ট একটু কম দেখা যাচ্ছে, মানে দেখা যাচ্ছে মোস্ট অফ দ্য বিমে মিনিমাম রিনফোর্সমেন্ট শো করতে যায়, এটা নিয়ে একটু মানে প্রবলেম আছে
বিমে মিনিমাম রিইনফোর্সমেন্ট
মোস্ট অফ দ্য বিমে স্যার দেখা যাচ্ছে, তাই এটা আর কি।
সেটা আসতে পারে, তোমার অ্যানালাইসিস থেকে যদি আসে তো কিছু করার নাই, ঠিক না?
মোটামুটি স্যার এই যে কি বলে এই 10 ইঞ্চি বা 16 ইঞ্চি বিম ধরছে স্যার, আমাদের স্প্যান মোটামুটি 10 থেকে 14 ফিটের মধ্যে স্যার বেশিরভাগই। স্যার ওই যে তারপরে স্যার মোটামুটি দেখা গেছে যে কি বলে এটা মিনিমাম রিইনফোর্সমেন্ট শো করে মোস্ট অফ দ্য বিমে। তো স্যার এটা একদম সমস্যা, মানে আমাদের কলাম রিইনফোর্সমেন্ট ঠিক আছে মোটামুটি।
10 ইঞ্চি বাই 16 ইঞ্চি তো অনেক, 14 ইঞ্চি 14 ফিট স্প্যান হলে তো গুড সেকশন দিয়েছো, ঠিক না? আর নিশ্চয়ই এই সেকশন তোমাদের বিল্ডিংটা সিমেট্রিক্যাল মনে হয়।
জি স্যার মোটামুটি সিমেট্রিক্যালি।
So, তোমাদের হয়তো টর্শনও খুব একটা নাই, ঠিক না?
জি স্যার নাইস তেমন একটা।
যার জন্য হয়তো তুমি you have only shear force, no torsion. That's why maybe your section satisfied.
আর স্যার ওই ইয়াতে কলাম
তোমাদের
স্যার মানে
কাজটা বাকি কাজটা কি দিয়েছে তোমাদের, মানে তোমরা এখন স্ট্রাকচারাল ডিজাইন করতেছো নাকি?
আপাতত স্যার শুধু আমরা ওই ই টাইপস মানে ইয়ার মডেলিংটা আমাদের মানে করতে দেওয়া হয়েছে।
মডেলিং
তোমার
এর
কি
ভ্যালু গুলো আসলে পরে স্যার ওরা আর কি ডিজাইনটা করে ফেলবে স্যার। এরপরে মেইন রিপোর্টটা তৈরি করবে স্যার, মানে আমরা আমাদের ক্লায়েন্টকে আর কি যে রিপোর্টটা দেই ওনারা যেটা দেখে আর কি কনস্ট্রাকশনের কাজটা শুরু করেছে।
এখন তো বিএনবিসি 2020 অ্যাপ্রুভালে তো তোমরা তো জানো এটা তোমাদের ডিজাইন রিপোর্টটা জমা দিতে হবে। হ্যাঁ
জি স্যার।
শারিয়ার শুনতে পাচ্ছ? হ্যাঁ
জি স্যার শুনতে পাচ্ছি।
ডিজাইন রিপোর্টে কি কি থাকে তুমি জানো এটা তোমরা?
ওই রিপোর্ট একটা মানে দেখছিলাম স্যার, একটু মানে ঠিক মানে ই নাই, মুখস্থ নাই আর কি, মানে দেখলে বলতে পারবো আমি।
তোমাকে মেইনলি আর মানে স্ট্রাকচারাল মডেলটা দিতে হবে, বিল্ডিং এর লেআউট গুলো দিতে হবে, বুঝতে পারছো? মানে প্ল্যান গুলো দিতে হবে, প্লাস তোমার মেজর স্ট্রাকচারাল মানে লোডিং, তুমি কি কি লোড অ্যাসিউম করেছো, লোড কম্বিনেশন গুলা কি কি, ম্যাটেরিয়াল প্রপার্টি গুলো কি কি, তারপরে টিপিক্যাল রেজাল্ট গুলো কিছু দিতে হবে আর কি। হ্যালো,
জি
তোমরা রিপোর্টটা তো করতে পারবা নাকি?
জি স্যার, ইয়ার রিপোর্টটা করা যাবে মোটামুটি।
রিপোর্টটাতে তুমি কোন কোড ইউজ করেছো সেগুলো লিখতে হবে আর কি, which code you followed and loading combination মানে কোডের রেফারেন্স দিয়ে then you have to write it. তোমাদের
স্যার
বিল্ডিং এর হাইট কত ধরেছো তোমরা?
স্যার আমরা ওই যে পার ফ্লোরে স্যার 10 ফিট করে ধরছি স্যার, তো স্যার মানে যার যেমন আসছে আর কি, মানে যার 12 স্টোরি তার 120 ফিট আসছে আমাদের এরকম।
120।
স্যার এক একটা
তাহলে তোমাদের
কমপ্লেক্স
মনে
স্যার
হয়
এক এক
লাগবে,
রকম ছিল
না?
স্যার।
মিনিমাম হাইট কত ছিল?
আমাদের স্যার ছিল 80 স্টোরি ছিল স্যার
8
মিনিমাম,
থেকে
আর
স্যার
হাইট ছিল
18
স্যার
স্যার আছে স্যার, 8 থেকে স্যার 18 তলা
তাহলে
পর্যন্ত।
সবারই লাগার কথা আর কি সামহাও, হয়তো বা যাদের 8 তলা বিল্ডিং ওদেরকে শেয়ার ওয়াল লেগেছে।
শিরল না দিলে স্যার ওই যে ডিফ্লেকশন বেশি আসছে স্যার আর কি।
হ্যাঁ তাহলে তো শেয়ার ওয়াল তো লেগেছে তোমার, তো ইউ ক্যান ইউজ দা শেয়ার ওয়াল ইন দা তোমরা কি ডুয়েল সিস্টেম ধরেছো?
জি স্যার ডুয়াল সিস্টেম ধরেছি।
তো সেখানে 25% চেক করে দেখেছো যে মানে ফ্রেম ক্যান টেক 25% অফ শেয়ার?
চেক করা হয় নাই স্যার, মানে আপাতত শুধু মডেলিং টাইপ করে রাখছি স্যার কি, বাকিটা
এটা তো চেক করতে জানো তো না?
না স্যার এটা একটু দেখালে ভালো হতো, মানে কিভাবে চেক দিবে
এটা এটা যেটা করতে হবে, তুমি বেইজের শেয়ার ওয়াল কতটুকু শেয়ার ফোর্স নেয় ওটা দেখবা, হ্যাঁ,
জি স্যার।
আর কলাম গুলা কত শেয়ার ফোর্স নিয়েছে ওটা দেখবা, ওখান থেকে ওটা দেখবা যে 25% আসে কিনা।
শিয়ার ফোর্স বলতে স্যার যে বেজ রিঅ্যাকশন স্যার, ল্যাটারাল রিঅ্যাকশন।
বেজ, হ্যাঁ বেজ রিঅ্যাকশন ল্যাটারাল, দুইটা ডিরেকশনে দেখতে হবে আর কি তোমাকে, দুইটা অর্থোগোনাল ডিরেকশনে। বুঝতে পারছো শারিয়ার?
জি স্যার বুঝতে পারছি।
তুমি ওখানে বেজে তুমি এগুলা দেখলে তোমাকে টেবিল করে দেখতে হবে আর কি, বা তোমার তো টেবিল হয়ে যায়, এই ট্যাবসে তো তোমার টেবিলে থাকে, ওখান থেকে তুমি যোগ করে দেখতে হবে আর কি যে তোমার টোটাল শেয়ার ফোর্সে 25% শেয়ার হল, সরি, ফ্রেম সিস্টেম নিতে পারতেছে কিনা।
জি স্যার, বুঝতে পারছি। স্যার
That
আমাদের
will
তো
need
স্যার
to-
মানে জিওটেকে বলা হয়েছিল যে আমাদের যে পাইল ফাউন্ডেশন ইউজ করতে হবে। স্যার আমাদের তো মানে পাইলের উপর কোনো মানে ক্লাস মানে কোনোদিন আমাদের হয়নি স্যার। তো এইটা কি একটু নেওয়া যায় একদিন, পাইল এবং পাইল ক্যাপ?
কেন তোমাদের পাইল ডিজাইন শেখানো হয়নি?
না স্যার, আমাদের শেখানো হয়নি এটা।
কেন? জিওটেকনিক্যাল ইঞ্জিনিয়ারিং এ তো শেখানোর কথা ছিল পাইল ডিজাইন।
স্যার পাইলের স্ট্রাকচারাল ডিজাইন নাকি?
পাইলে মেইনলি যেটা যেটা আসে ধরো জিওটেকনিক্যাল ডিজাইন তো শিখাইছে নাকি?
জি ইয়াতে যেটা
Using the end bearing and skin friction, so you have that. Then structural design আমার মনে হয় তুমি স্ট্রাকচারাল ডিজাইন বাইলে আমাদের টোটাল তো কতটুকু কম্প্রেশন আসতেছে তুমি তো জানোই, জানো না?
এটা কিছু শুধু ওই যে অ্যাক্সিয়াল মেম্বার হিসেবে ধরবো স্যার পাইলটা?
হ্যাঁ হ্যাঁ, তোমার তো জানা আছে তো একটা পাইলের লোড কত আসে। Then you can you have the reinforcement, then you can calculate what will be the capacity of the pile.
এটা পাইল ক্যাপটা কি করবো স্যার? পাইল ক্যাপ
পাইল ক্যাপটা যেটা করতে হয় হবে তোমাকে, পাইল ক্যাপটা তুমি পাইল থেকে যে রিঅ্যাকশন গুলো আসতেছে না, ধরো প্রতিটা পাইলের যে ক্যাপাসিটি আসতেছে সেটা
জি।
তুমি পাইল ক্যাপের উপরে অ্যাপ্লাই করতে পারো আর কি। অ্যাপ্লাই করে দেন ইউ ক্যান ক্যালকুলেট দ্য মোমেন্ট এন্ড ইউ ক্যান calculate the shear force and you can do the design.
সেটা কি তাহলে ওই যে বিমের মতো করে ডিজাইন করবো?
হ্যাঁ ধরো আমি তোমাকে বলি, ধরো আমার একটা পাইল ক্যাপ, নিচে মাঝখানে কলাম আছে, ঠিক আছে, দুই পাশে দুইটা পাইল আছে, তাহলে মানে আমি যদি এটাকে আইসোলেট করি তাহলে দুইটা পাইল থেকে কি লোড আসবে? দুইটা ভার্টিক্যাল লোড আসবে, ঠিক না? একটা ইনভার্টেড একটা বিমের মতো। হ্যাঁ শারিয়ার, বুঝতে পারতেছো? হ্যালো,
জি স্যার, বুঝতে পারছি।
জানি মাঝখানে কি থাকবে? মাঝখানে কলামের থেকে লোড আসবে, ধরো 100 টন লোড আসলো কলাম থেকে মাঝখানে, আর পাইল থেকে কত আসলো? ধরো 50 টন দুইটা লোড আসলো। দেন ইউ নো দা মানে ডিস্টেন্সেস, তুমি তো যে পাইলের ওখান থেকে তুমি ইউ উইল আন্ডারস্ট্যান্ড দা হোয়াট আর দ্য ডিস্টেন্সেস বিটুইন দা center line of the columns to the pile center. Then you can draw the moment diagram, you can draw the shear force diagram, and finally you can do the design.
স্যার এটা ট্রায়াঙ্গুলার পাইল মানে তিনটা পাইলের যে মানে এটা ক্যাপটা বা যে চারটা পাইলের যে ক্যাপটা, সেগুলো মানে মানে এটা অ্যানালাইসিসটা কিভাবে করবো?
ট্রায়াঙ্গল যদি হয় তুমি তুমি যদি চারটা যদি হয়ে থাকে সেক্ষেত্রে হয়তো তোমাকে বাই হ্যান্ড তো আর তুমি তখন সেটা করতে পারবে না, তোমাকে তখন হয়তো আমি হয়তো যেটা করতাম, আমি হয়তো ধরো চারটা যদি হয় পাইল, হ্যাঁ, তাহলে চারটা ফাইল থেকে কত লোড আসবে? ধরো 50 টন যদি করে হয় তাহলে কত আসে? 200 টন, 200 টন আসে না?
জি স্যার।
এই 200 টন আমি হলে আমি এভাবে করতাম, আমি এটাকে ইউনিফর্মলি ভাগ করে দিতাম চারিদিকে, বুঝছো কথাটা? আমার কাছে তো এরিয়াটা জানা আছে না?
জি।
I know the area, though I can give into the pressure as the pressure. বুঝতে পারছো নাকি? ইউনিফর্ম, you can give as uniform pressure. Then you can analyze the using the the তুমি যদি স্ট্রিপ নিয়ে তখন অ্যানালাইসিস করতে পারো।
জি স্যার। আর ওই যে পাইলের সেন্টার বরাবর করতেছে মানে তখন কোনো যে কি বলে স্ট্রং ব্যান্ড?
এটা একটা assumption আর কি, you assume that it will be distributed uniformly along the মানে total area of the pile cap আর কি।
জি স্যার, তাহলে এটা আমরা ট্রাই করে দেখবো স্যার ইনশাআল্লাহ।
ওইভাবে you can, this is one of the way you can do it, হ্যাঁ। আর অথবা তুমি টোটাল তাহলে তোমাকে 3D অ্যানালাইসিস করতে হবে আর কি। in that case if you want to do that, then you have to go for, if you want to do very in-depth analysis, you have to go for FEM. You draw the pile cap and you have to do the analysis. I think that will be very complicated for structural design. Normally you have to use the simplified methods. Any বুঝতে পারছো নাকি বুঝতে পারো নাই?
জি স্যার, বুঝতে
আমাদের
পারছি।
বিএনডিসি তো ওইখানে পাইলের মিনিমাম ডাইমেনশন এখন দেওয়া আছে, পাইলের রেইনফোর্সমেন্ট দেওয়া আছে না?
জি স্যার, আছে।
তো ইউ জাস্ট ফলো দ্যাট।
জি স্যার।
ওখানে তুমি দেখো একটা টেবিল দেওয়া আছে, কতগুলা কত পার্সেন্টেজ স্টিল দিতে হবে, কয়টা সংখ্যা বার দিতে হবে, you can get it, and of course you can check what is the capacity of the pile.
জি স্যার, বুঝতে পারছি।
So any more questions? তোমরা এখন শেয়ার ওয়াল ডিজাইন করতে পারবা তো নাকি?
জি স্যার, পারবো ইনশাআল্লাহ।
মেইনলি তোমাকে হয়তো you may need to provide the boundary element or depending on your movement. Of course you have to provide the shear reinforcement both longitudinal and transverse directions, and your minimum reinforcement requirement is 0.25% for in the case of shear wall. So of course I think you need to satisfy that. So if you have no questions, so we want to conclude here, Harun.
Yes sir. আচ্ছা স্যার। Sir.
No questions from other student except Shariar.
শাহরিয়ার বাদ আর কারো কোনো কোয়েশ্চেন আছে? রেদওয়ান, বাঁধন, অর্পণ, ইস্তি, কারো কোনো কোয়েশ্চেন? না স্যার, মনে হয় আর কারো কোনো কোয়েশ্চেন নাই স্যার। তো ওদের আর কি মডেল তৈরি করা হয়ে গেছে তো স্যার, এরপর ওরা ডিজাইনটা করে ডিজাইন রিপোর্ট আর কি তৈরি করে ফেলবে স্যার। আর ওরা প্রপোজালটা দিয়েছিল, ওদেরকে ওইটার জন্য একটা প্রেজেন্টেশন তৈরি করতে বলেছি স্যার আর কি। তো ইনশাল্লাহ সবকিছু হয়তো বা আগামী 2 উইকের মধ্যে রেডি করে ফেলার চেষ্টা করবো স্যার।
তাহলে তুমি একটু মনিটরিং করিও আর কি ওদের
জি
সাথে।
স্যার, আমি মনিটরিং করতেছি স্যার, ওরাও আমার সাথে স্যার রেগুলারলি যোগাযোগ করেন স্যার, বিভিন্ন সমস্যার কথাও বলে। ইমরান স্যারও আছেন, সাইমা মিসও আছেন, তো সবাই মিলে ইনশাল্লাহ আমরা স্যার দেখতেছি সবকিছু।
ওদেরকে এখানে একটু ইনভেস্টিগেশন আনার জন্য।
জি স্যার, ইনভেস্টিগেশন তো স্যার বলেছিলেন স্যার। জি স্যার।
হ্যাঁ, ওদেরকে ওটা আনার জন্য একটু শেয়ার ওয়ালের থিকনেসটা তুমি একটু ভ্যারি করে দেখতে বলিও আর কি।
আচ্ছা স্যার, আমি বলবো না স্যার, শেয়ার হলে থিকনেস স্যার
একবার হয়তো
কমায়
12
বাড়ায়
ইঞ্চি
দিতে
করলো,
হবে।
10 ইঞ্চি করলো, 8 ইঞ্চি করলো। হ্যাঁ,
জি স্যার।
তাহলে ওরা একটু কিভাবে একটা মিনিমাম থিকনেসে আসা যায় জিনিসটা
জি স্যার,
শিখতে
থিকনেস
হবে।
অপটিমাইজেশনটা বুঝতে
হ্যাঁ,
জি।
ওইটা একটু আনার চেষ্টা করি আর কি।
জি স্যার।
তো ঠিক আছে না, থ্যাংক ইউ সো মাচ।
জি স্যার, আসসালামু আলাইকুম স্যার।
আসসালামু আলাইকুম স্যার।
আমি তোমাদের সাথে ভিডিওটা শেয়ার করে দিব আজকে, ঠিক আছে? আর স্যার আমার সাথে স্লাইড গুলো ম্যাটেরিয়াল গুলো শেয়ার করলে ওইগুলো শেয়ার করে দিব ইনশাআল্লাহ। ওকে, আল্লাহ হাফেজ। হ্যাঁ।